Hello children, once again welcome back to Physics with Sanu. See, in this video we are going to discuss the past questions from the chapter Kinetic Theory. This is a very simple chapter and you can expect one question definitely from this chapter. Okay, in the given VT diagram, what is the relation between P1 and P2? P1 and P2. See, here we have volume plotted along y-axis and temperature plotted along x-axis. Okay, we have the ideal gas equation that is PV equal to nRT. Okay, so this volume V that is equal to nR divided by P into T. See, while plotting an equation, you have to replace the quantity plotted along the x-axis by x and quantity plotted along the y-axis by y. Here volume is plotted along the y-axis, so let me replace this V by y. The quantity inside the bracket is a constant and T is the quantity plotted along the x-axis, so let me replace this by x. So we will get y equals quantity inside the bracket, that's a constant, into x. Okay, so that is just like y equal to mx plus c. Instead of c we have nothing, or c is equal to 0. See, y equals mx plus c is the equation of this line, that m is the slope of the line and it is equal to tan theta, where theta is the angle made by the straight line with the positive direction of x-axis. Okay, and this c is the y-intercept. Okay, y-intercept. Here we have 0, so y-intercept is 0. Means the line must be passing through the origin. Okay, now see, we have, this is the slope, nR by P, that is the slope. See, angle made by a line with the positive x-axis is theta, then its slope is tan theta. As theta increases, tan theta increases. Here the slope is nR by P, of which nR is a constant, so tan theta or slope is proportional to 1 by P. So when theta is more, tan theta will be more and P will be less. Here we have theta 1 and theta 2. Theta 2 is more, so P2 must be less. Okay, so P2 must be less than P1. Okay, P2 less than P1, right? Now let's see what we have. The equation of state corresponding to 8 gram of oxygen. Number of moles will be mass by molar mass, 8 by 32, that is 1 by 4. So PV equals RT by 4. Okay, PV equals RT by 4. Okay, the temperature of a gas is minus 50 degrees Celsius initially. To what temperature the gas should be heated so that the RMS speed is increased by 3 times? Okay, see, we have the expression for the RMS speed of gas molecules. It is under root 3 RT over capital M. Capital M is the molar mass and T is the absolute temperature. So V RMS is directly proportional to square root of temperature. So temperature directly proportional to square of V RMS. See, T directly proportional to square of V RMS. Now see, RMS speed is increased by 3 times. Means it will become 4 times. Okay, so T dash by T, that will be V dash by V whole square. V dash final RMS speed, that is 4 times. So 4V by V whole square, or it is 16. So T dash we will get 16T. Original temperature is minus 50 degrees Celsius, but this T must be in Kelvin. So to convert minus 50 to Kelvin, you have to add 273. So minus 50 plus 273, that will be 223. So the final temperature will be 16 into 223. You need not multiply this. See, if you multiply this at the unit place, what you will get? See, 6 into 3, that is 18. So at unit place you will get 8. Children, if the temperature, final temperature is in Kelvin, at the unit place there must be an 8. Okay, see, we have 2 choices in Kelvin. One is 3097, there is no 8 at the unit place. Okay, and the next is 223, here also there is no 8 in the unit place, right? Okay, so these two are not the correct option. Now see, if the temperature is in Kelvin, at the unit place we will have an 8. If you want to convert it into degrees Celsius, you will have to subtract 273. Means at the unit place you will have to subtract 3. 273 means 3 at the unit place from 8. If you subtract 3 from 8, there will be or there should be 5 at the unit place if the temperature is expressed in degrees Celsius. Okay. Degrees Celsius, there must be 5. See, there is only one choice. Okay, that is 3295. Okay. Now, children, suppose you want to multiply this 223 with 16. Okay, but this 223 you can express it as actually 225. See, you need not express anything. See, all this you have to do mentally. Okay, mental calculation. This is actually 225 minus 2. Okay, so this is 16 into 225 minus 32. Okay, and see, this is 16 into 225. See, you double 225, then you will get 450. Again double it, you will get 900. So 900 is actually 225 into 4. Okay, then actually you have to multiply by 60. Already you have multiplied by 4. You got 900. Now you have to multiply this 900 with another 4. Multiplying 900 by 4 is very simple, and that will give you 3600. Okay, 3600. To convert, it is actually this part, 3600 minus 32. Okay, that will give you 3568. Okay, if you want to convert it into degrees Celsius, again you will have to subtract another 273 from it, right? That will definitely give you 3295. Next, see, in a vessel, the gas at pressure capital P, if the mass of all the molecules is halved and their speed is doubled, then the resultant pressure will be. See, pressure is given by 1 by 3 N, that is the number of molecules per unit volume. M is the mass of each molecule, and C, V square, that is the square of the RMS speeds. So P dash, that is 1 by 3 N, remains unchanged, but mass is reduced to half, and the velocity, that is doubled. So 2V whole square. Okay, so here we will get 4 and here we will get 2 in the denominator, so the pressure becomes 2 times or 2P. Okay, the temperature of a gas is raised from 27 degrees Celsius, that is 300 Kelvin, to 927, means 900 Kelvin more. So it will be 300 plus 900, that is 1200. Initial temperature 300, final temperature 1200. Okay, so V is again root of 3 RT by M, and V dash by V will be root of T dash by T, that is 1200 over 300. That will be root 4, or it is equal to 2. So V dash equal to 2V. So the speed gets doubled. Okay, now the relation between pressure capital P and energy density of a gas. See, pressure is 1 by 3 rho V square and energy density is half rho V square. Okay, and see, from here rho V square can be 2E. So replace this rho V square by 2E. So we will get P equals 2 by 3E, where capital E is the energy density. So this must be the correct option. Okay. See, a expression, see, we have to get the expression 1 by root 2 pi n d square. 1 by root 2 n pi d square. Okay. A gas mixture consists of 2 moles of oxygen and 4 moles of argon. So total number of moles in the mixture must be 2 plus 4, 6. Okay, total number of moles 6. Now see, neglecting all vibrational modes, I mean you have to consider only the translational and rotational degrees of freedom, the total internal energy. See, this is the expression for the internal energy, U equals NFRT by 2. Then how do you find the number of degrees of freedom for a mixture? See, here is the formula. Number of degrees of freedom F is N1 F1 plus N2 F2 divided by N1 plus N2. Here we have 2 moles of oxygen which is diatomic with 5 degrees of freedom. Okay, so 2 into 5. 4 degrees of argon, that is an inert gas. So it is monatomic, must be having 3 degrees of freedom only. So 4 into 3 divided by N1 plus N2 is 6. So we will get 11 by 3. Okay, now let's find the internal energy. See NFRT by 2. See that 1 by 2 half I have written first. Then the number of moles is 6. Okay, degrees of freedom I have got 11 by 3. Okay, then capital R and T. Okay, so this 3 into 2, 6. 6 and 6 can be cancelled. So we will get 11 RT. So this must be the correct option. Now the ratio of the specific heats Cp by Cv gamma in terms of the degrees of freedom N. Okay, see gamma is 1 plus 2 by F. Here it is given that the number of degrees of freedom F is represented by N. So it must be 1 plus 2 by N. Okay, 1 plus 2 by N. Right? Now the molar specific heats of an ideal gas at constant pressure and volume are denoted by Cp and Cv. Gamma is Cp by Cv and R is the universal gas constant. Then Cv is equal to. See here we have the Mayer's relation Cp minus Cv equal to capital R. Let's divide throughout by Cv. So Cp by Cv, first term, that will be gamma. Okay. And the next term will be Cv by Cv and it is equal to 1. So gamma minus 1 on the left side. And on the right side we will get R by Cv. Now take this Cv to the left and gamma minus 1 to the right. So we will get Cv equals R divided by gamma minus 1. So this must be the correct option. Okay. Yeah. If gamma be the ratio of specific heats for a perfect gas, the number of degrees of freedom of a molecule of the gas is. See, we have gamma equals 1 plus 2 by F, where F is the number of degrees of freedom. When this 1 is taken to the left, we will have gamma minus 1 equals 2 by F. Okay, and F will be 2 by gamma minus 1. That is the number of degrees of freedom. 2 divided by gamma minus 1. Okay. Now see the degree of freedom of a molecule of triatomic gas. See, for any system, the total number of translational degrees of freedom is 3 always. Means along the x direction, y direction and z direction. Okay, 3 degrees of freedom. Okay, translational degrees of freedom will be 3 for any system under any condition. Okay. And see for monoatomic no rotational degrees of freedom. So note it will have only the translational degrees of freedom, that is 3. See for diatomic, if we neglect the vibrational mode, see total number of degrees of freedom will be 5, of which 3 are due to translational motion and the remaining 2 due to rotation. Okay, for polyatomic, if the molecule contains more than 2 atoms and if the structure is linear and if we neglect the vibrational mode, then the number of degrees of freedom will be 7. Again, 3 are due to translational and the remaining 4 are due to rotation. For polyatomic means molecules containing more than 2 atoms, and if it is non-linear, the structure is non-linear, then the number of degrees of freedom is 6. It contains only 3 translational and 3 rotational degrees of freedom. Okay, vibrational here also we have not considered. Okay, this is the number of degrees of freedom in general. See here we have a polyatomic or it is a triatomic. Okay, so if it is linear, number of degrees of freedom 7. If it is non-linear, number of degrees of freedom 6, but it is not specified whether it is linear or non-linear. See, but in the options we do not have an option that is 7. Okay, so the only possibility is 6. Okay, now here we have a beautiful question, that is if for a gas R by Cv is 0.67, it can be written as 2 by 3. The gas is made up of molecules which are, see, R by Cv is 0.67 or 2 by 3 and we will get Cv equals 3 by 2R. See for the, see the general formula for Cv, that is F by 2R. So F by 2R is given as 3 by 2R. Means F, the number of degrees of freedom is 3. So the gas must be monoatomic. Okay, gas must be monoatomic. Right? So 1 mole of an ideal monoatomic gas requires 207 joule heat to raise the temperature by 10 Kelvin when heated at constant pressure. See, molar specific heat capacity is delta Q heat added divided by number of moles and change in temperature. Okay, this is 207, number of moles is 1 and change in temperature is delta T. So molar specific heat capacity at constant pressure will be 20.7. Okay, how much heat will be required to raise the temperature by 10 Kelvin when heated at constant volume? Okay, so heat required at constant volume delta Q dash, that is NCV delta T. Okay, number of moles is again 1. CV we have got CP minus R. CP is 20.7 and R, that is 8.3. It's given 8.3. So 20.7 minus 8.3 will be 12.4. Okay, so 1 into 12.4 into change in temperature required is 10. So it will be 124 joule. 124 joule. Okay.